Last time, our topic was the algebraic geometry of tensor networks, and we spent a lot of that time just defining those terms. So we had crash courses on algebraic geometry, on tensors, and on networks, and how to learn something about that geometry. So let's just review what we talked about yesterday. So tensors are multi-way arrays. This one's three-way array, 3 by 3 by 3. And they can be thought of as a table of numbers, a table of entries. They represent a multilinear transformation from, say, the yellow space to the red space, from a tensor product of vector spaces to a third vector space. And thinking of it as a linear transformation like that, any particular choice is like a flattening of the tensor. Thinking of it as a matrix, even though it's naturally something more complicated. And it's equipped with a multilinear action on each side. So, there's a way that the change of basis acts, and it acts differently on all of these legs because they're different vector spaces. So it has to act differently, even if they happen to be the same dimension. We saw that tensor decomposition is something which is possible, but it's a more subtle question than just matrix decomposition. And we could think about tensor networks or graphical models as examples of a strategy for tensor decomposition, and one that's been very successful, of course. And we argue the data arrives in tensor format and that we lose something by flattening it down to a matrix. So there were some good questions after the talk yesterday, and I gave comments that answer them, but I want to put up a couple of slides that make a little bit more explicit the way in which things get harder when we move from the matrix case to the tensor case. There's lots of things you'd think would be okay. They stop being okay. So here's one basic question. So suppose we have this kind of action where on every leg I act by a change of basis, and I'm allowed to choose a different change of basis for each leg. In the best case, we have only finitely many orbits, right? So in the matrix case, this is easy. The orbits just correspond to the rank of the matrix. I can diagonalize the matrix, and up to, if I do an SVD, I can characterize the space of different matrices by how many non-zero singular values there are. Okay, that's like I do a change of basis on each side of the matrix. There are only finitely many orbits, one for each rank. So if it's an n by n matrix, there's n plus 1 orbits, right? And they degenerate into each other. So in the tensor case, that is only true for very small examples. So this is worked out by there's a paper by Katz, and then there's some papers by Parfanov, a student of Wimberg, that work this out very explicitly. And this is one of those things that's been sort of rediscovered maybe 3 or 4 times in literature. And this just says up to about sort of 236, the number of orbits under this change of basis on each leg is finite. And then when we get to things that are bigger than that, they stop being finite. So we're so different from the matrix case that there isn't even a characterization like rank to explain all of the different orbits as we change basis. So, and if you think about it a little bit, that's clear by just thinking about just counting parameters. As soon as you get a really big cube, you just don't have enough parameters in all these change of bases to actually change anything. So that's one way in which you can see that things are going to get more complicated in the tensor case. Another really simple way is just say, well, here's a matrix that I've flattened, I've turned into a vector. Can you tell me what its rank is, or its SVD, or its kernel, right? No, so it's kind of the same way with tensors, right? If we take some complicated thing and we forced it into a smaller dimensional or smaller way thing, we destroyed a lot of structure. There's a lot of things that are important to us that we can't tell anymore. It's just the same as how a matrix and a vector are not really the same thing. Okay, so given these tensors, we can combine them to build tensor networks for graphical models. We can connect the wires to compose or contract, just glue this tensor to that tensor to that tensor, and that essentially just means matrix multiplication, right? I'm composing the linear maps, or I have something more complicated, I think about them as linear maps, and I glue them together along whichever wires I like. And I can juxtapose them to take the tensor product of the maps, the Kronecker product of the matrices that represent them, or to run these things in parallel. And a combination of these operations allows me to build up complicated networks. And I may need some additional special morphisms, some special maps and things like that. Like being able to cross wires, that's a swap. So we talked to someone yesterday about braided monoidal categories being a good way to write down deep belief networks. So we combine these things into tensor networks, and we get recognizable objects like Bayesian networks, which we can change into a factor graph representation, and with a little bit more tweaking, a representation that looks like one of these tensor diagrams I've shown you, or a string diagram is the technical term for this type of picture. Okay, so we had a 5-slide course in algebraic geometry. Today we'll have, I think, a 1-slide course, just a refresher. So in algebraic geometry is the study of solutions to systems of polynomial equations. If I consider a ring of multivariate polynomials, so an f is a polynomial just with coefficients in some field and indeterminants x1 up to xn, which you could think of as, say, probabilities. So in this example, we had instead of x1 up to xn, we had p sub all possible bit strings, right? And so these were the probabilities of different the different probabilities of different outcomes on the visible variables. We could take the zero locus of a set of polynomials, script f, all of the points in the ambient space on which those polynomials vanish, on which all of those polynomials vanish defines the variety v of f. And if I give you just a set that sits inside this space, like the image of my model map, or a set of probability distributions, which is inside the simplex, and so it doesn't have infinite extent, then I can define its vanishing ideal as just the set of all polynomials that vanish on every point. Hilbert's basis theorem tells us that such an ideal is a good description in the sense that there's a finite generating set for it, and a lot of computational algebraic geometry works by getting such bases, such like Grosvenor bases, universal Grosvenor bases and things like that, and the nice properties have some sorts of nice combinatorial properties or nice computational properties. So there's an algorithm to do this, which is the common generalization of polynomial division, if you've ever done that, and Gaussian elimination. And that produces such sets of such generating sets. And if I give you a set S and Cn, it has a Zariski closure, which is I take all the polynomials that vanish on it, then I take all the points on which those polynomials vanish, and that's a variety. Okay. So if we're handed a polynomial map from parameter space to an ambient space, then we would like to figure out the algebraic properties of its image. So one thing I sort of glossed over yesterday, right, is that a lot of the time our maps in machine learning are not given as polynomial maps, right? They're given as terms of an exponentiation. So you just have to pull through instead of adding, multiply something to an exponent, and then, so if you do that and sort of do it a little bit carefully, you can transform one of these exponential maps into a polynomial map, like a log linear map into a log linear model into or an exponential family into a polynomial map. Okay. We have a parameter space and we get it into an ambient space. And the example is the parabola. The parameter is t. I can set x equal to t and y equal to t squared. And then this defines an image of this parameter space. And we'd like to know what are the equations that define this set and what are the inequalities that appear. And since this thing sits inside of a simplex, we know there's going to be some kind of inequalities that we're going to need too. But it's even worse than that. There are inequalities that come from the parameterization itself. And y minus x squared cuts out this image. We don't need any inequalities in this case. And so this process is called implicitization. Okay. First new slide. So algebraic geometry and tensor networks. So from the point of view of algebraic geometry, if I write down one of these tensor networks in this representation or in one of the other representations, I write down a graphical model that shows up in machine learning, signal processing. I write down things that show up in computational complexity, like constraint satisfaction problems, weighted constraint satisfaction problems, or circuits where I'm allowed to use families of gates. These things describe a regular map from the parameter space, so a choice of tensor at each of the nodes, a choice of parameters, to some ambient space, which is our probability space. And the image is, you could think about as the variety of representable probability distribution. So the set of all things that I can explain with this model, or I can represent with this model, has the structure of an algebraic variety. So we should use this technology to help understand what's going on. Now this map has fibers. So if I have a map from some parameter space to some ambient space, and I get some variety that's the image of this map. I could take a point on that variety, and it could be that the preimage of that point is a point. It could be that the preimage of that point, the sets of parameters that give you that point, are a collection of discrete finite points, a finite collection of points, or it could be that it's itself a variety, or itself a, that's not a very good drawing, let's draw it like this. And that's why it's called a fiber, because it kind of is like, it's like a line of things that go above that. Okay. So these fibers tell us questions about identifiability. So identifiability says if I pick a point here, is there only one? Okay. It could be finite to one, and it could be this kind of thing. It tells us about transferability. So if I have if I have multiple models modeling the same thing but using different parameters, maybe because there's this freedom here, how do I transfer my representation from one model to the other? Yeah.
What do you mean by regular map?
Just a technical definition. Basically, you think of it as a polynomial map on the ambient space. Sometimes it's just a rational map, too. So transferability, so if we want to be able to take our parameters that we learn from one model and transfer them to the other, or we learn multiple parameters by finding a lot of local optima, and we want to say that they're all the same in some sense, that's kind of a question about the group that acts on this fiber, or the symmetries of this fiber. And it also turns out, as I'll talk about at the very end, that these fibers can tell us something about learning rate, generalization error, performance of the model. If you're in a situation where there's only one, and all of a sudden there's a whole bunch, if you're near the neighborhood of things where there's a lot of different parameters that help, that solve your problem, things tend to get worse. Okay. So the main thing I want to talk about today is, or this morning, is algebraic strategies for describing graphical models. So we gave the basic principles of doing this last time, and now I want to get into a little bit of details about the kind of things that we know about. And first, what I need to do is just review the definitions. And of course, everyone has a different point of view on what, sometimes we all know this definition, but of course we all think about it a little bit differently. If you're really a computer scientist, algorithmic, sometimes the definition of the model is the program, right? I mean, it's the algorithm that you run. For a mathematician, the model always is some mathematical object, and then we have an algorithm to optimize that. We have an object, an optimization function, or an objective function, and an algorithm. And we like to try to separate those things. And so mostly what I want to talk about is just the model. So I just want to make sure that I specify what I mean by the model. So this is this philosophy of algebraic statistics. We want to think about our models as algebraic varieties. What distributions can be represented by the model? What is the geometry of the parameterization map? And what are the implications? Okay, so here's a hierarchical model or an undirected graphical model. So this is defined by, an undirected graphical model is defined by an undirected graph, and a hierarchical model is defined by a simplicial complex. And not all undirected graphical models are hierarchical models, but not conversely. So we have n random variables, x1 up to xn, and I'm thinking them all as having finitely many states. So there's a way to adapt this technology to the Gaussian case, but I don't want to talk about that today. It'll take us too far afield. We define dependence, we have a notion of local interaction. We define dependence locally by a simplicial complex, and that parameterizes a family of probability distributions by potential functions or factors, so one per maximal simplex. So another way of saying is we just have, these things are grouped into factors. I can think about it as a bipartite graph. Right? I have a factor. These things interact through that factor, and otherwise don't interact with the rest. An undirected graphical model has a special simplicial complex. The simplicial complex is the clique complex of the undirected graph. So here's an undirected graphical model. It has two cliques, this one and that one. For each clique, two maximal cliques. For each clique, I associate a factor. And that is, this is also a diagram of the simplicial complex in terms of its maximal elements. So every undirected graphical model, by definition, has this simplicial complex associated to it as its factor graph. But there are factor graphs like this one, which has no three-way interaction, which has where there's no graph such that would give this as its simplicial, as its clique complex. Right? Okay. So this should be familiar if you've been working with graphical models. And it defines a family of probability distributions on our discrete random variables by just taking the product of all of these factors. So C sub S. I like C because it looks kind of like a square, particularly if you have a serif font in it. So that represents one of these factors, C sub S, and then the state of all the variables restricted to S. It's just a product of those things, and then I have to renormalize it by the partition function, so the sum of all of these things in order to turn it into an honest probability, right? So each of these things is our little tensor factor. That's the probability distribution. And it defines a factor graph, as we've been seeing. This is just the bipartite graph of nodes, factors, and edges. I'm going to allow hidden variables, denote them by, say, an open disk and a filled disk for visible variables. And every maximal simplex in this factor graph is denoted by a box and is connected by an edge to each variable that is included in this maximal simplex. Okay, so there's some combinatorial data that defines this thing. Here's one with a hidden node added into it. Okay, and of course, hidden nodes make things much harder. In the undirected case, without hidden nodes, hierarchical models correspond to exponential families, or what geometers call toric varieties, and these things are wonderful. So they have, if it's a true toric variety, there's all of these defining equations, instead of being potentially 5 trillion monomials, have 2 monomials. Okay, so they're binomial ideals. They're just something times something else, and there's nice ways of explaining what those are. So in the toric case, things are much easier. Unfortunately, that thing is not closed under marginalization, so in general, we want to include hidden nodes. And from a point of view of, if you sort of believe there's something interesting about this category theory stuff, anytime we want to allow sort of contractions, composition, we're going to have to allow hidden variables as well. So if we want to sort of get something which is universal in that sense, we want to allow that. Okay. So you might know about the Hammersley-Clifford theorem. So the Hammersley-Clifford theorem relates probability distributions that factor according to an undirected graphical model and Markov properties of that graph. So the simplest way of thinking about that is just graph separation. This node is independent of this node, given the nodes in between, if there's no path between those things. Right? So you can translate the Hammersley-Clifford theorem into a statement about algebraic geometry. It's a theorem about implicitizing undirected graphical models that takes your parameter map and transforms it into an ideal by associating basically each of these conditional dependent statements to a module of equations. So Hammersley and Clifford delayed publications for many years, actually I think it's like 5 years or something like that, trying to deal with the non-negative case, right? So this paper is about when all the probabilities are positive. So you're in the interior of the simplex. And it was Geiger, Meek, and Sturmfell's, this paper, toric algebra of graphical models. By taking the algebraic point of view, they were actually able to sort of complete this theorem and say what happens in the non-negative case for undirected graphical models. And so that was, to me, a sign that this is sort of a powerful technique for understanding what's going on. Of course, in general, I mean, one of the things that happens here, with the Hammersley-Clifford theorem is that we have, for undirected graphical models, we have this wonderful notion of conditional independence that sort of organizes our understanding of the ideals. So it organizes our understanding of the test for membership, or when can something come from this model if it satisfies these conditional independent statements, right? And I mentioned a little bit yesterday that sometimes there's representation theory we can use to organize these things. But in general, we just get these messes of polynomial equations, and sort of lurking out there's some theory like conditional independence that turns it into something nice and combinatorial and accessible to humans, but we just don't know what that theory is yet. Okay, so another definition, Bayesian networks. So again, I'm going to do this just in a combinatorial way. We have a directed acyclic graph. We have hidden and visible variables. The vertices n are partitioned into these hidden variables and visible variables. And each of these variables has some number of states. Of course, the parameterization defines for each variable a conditional probability distribution, so a stingless stochastic matrix probability of the variable I being in state x sub I given the state x sub parents of I of its parents. And then we write the probability distribution before marginalization. We're just taking a product according to this topological order. Right? We pick a root, and then we just multiply all of these conditionals. And then if we want to marginalize out some of the nodes, we have to sum over the hidden nodes. And we don't need to do a global normalization by the partition function because we've done the normalization locally at each of these factors. And doing this kind of normalization corresponds geometrically to sort of having multiple projective spaces sitting around, or multigrading on the algebra, if you know about that. Okay, so we talked about how every Bayesian network can be written as a directed factor graph model. So I can change that, but not the other way around. And there's another paper that was sort of laid down the foundation of thinking about these things, Bayesian networks in terms of algebraic geometry, and that's Garcia, Stillman, and Sternfels, 2005. So I just wanted to give you the pointer to those papers in case you wanted to get a good starting point for this stuff. Okay, so this is a conference about deep learning, so let's define our deep belief network. So of course, there's a cat and mouse game where the technology and the new models are constantly evolving. And if you're sort of a mathematician that's trying to make a precise statement about the models, I'm kind of like running after you guys, right? I'm trying to look at the models that you've developed and take a simplest version or take a version that I can get my hands on. So this is the version of deep belief networks that I like to think about. All the nodes are binary. It's completely defined by the tuple of layer widths. So how many nodes do I have in the visible layer? How many nodes do I have in the next layer, and so on? So there's some L, which is the height of the network, or the depth of the network. And then I have this tuple of layer widths, and that completely defines the model. Okay, so I haven't included, for example, sparsity things. I haven't talked about the priors or anything like that yet, right? So we're just thinking about this as a space of probability distributions, as this sort of object. So of course I can think about it as an unhidden thing. So if before I hide all of the top rows of variables, it defines a probability distribution, which is just, so H0 here is just the same as the visible. This is the visible layer. The probability of the whole stack can be computed as the probability of the associative memory on the top, the RBM, and then the product of all of the conditionals. And we know how to compute, or we have a specified form for all of these things on the inside. And these things are just the state of each of the units. And the parameters are the connection weights between units j and I from the k minus 1th and kth layer. And I have a bias weight 1 per layer. Okay. And then the deep belief network model, which is again also specified completely by this tuple, is just the marginal of that, so where I sum over all of the top nodes, everything except the visible layer. And it has a lot of parameters, right? Sometimes millions of parameters in practice. And so I keep arguing that one of the most basic questions you can ask about these models are things like identifiability and dimension, right? So if we're sort of very lucky, or we haven't wasted parameters, this thing is the expected dimension of our deep belief network, right? So as a space of probability distributions all the way in the bottom, if it's not too long, if it doesn't do anything silly like bottleneck down to a tiny thing and then come back out, then there's no collapse or waste of parameters. And so one of the most basic questions you can ask is which architectures or which tuples, n0 up to nl, have this expected dimension, right? So for which ones are no parameters wasted, if you like. And that's one sense in which some models might be able to dominate others, right? So if you have two models that have the same dimension and represent the same space, but one uses many, many more parameters, maybe it's more efficient to use the one that's more direct. Okay, so let me talk about what we understand. So where we are in this project of understanding models, graphical models as algebraic objects. Well, the deep belief network is in some sense the culmination of a bunch of different models. So there are a lot of models we know about, and the deep belief network contains a lot of those models. So that's kind of a good news, bad news scenario, right? So on the one hand, we can say something about it because we can talk about a bunch of things it contains, but on the other hand, we're unlikely to be able to solve it without having solved all of the stuff inside. Okay, so we don't have a complete semi-algebraic description of deep belief networks or deep Boltzmann machines. We certainly do have some partial information about representational power that you may know about from a lot of other papers by other authors. And we do have also algebraic and semi-algebraic descriptions of these submodels. So, and that's what I'm going to talk about next. So we have descriptions of naive Bayes models, which is just that one hidden node, lots of visible nodes. Hidden Markov models, tree models, restricted Boltzmann machines, et cetera. So all of these things we thought of as lying inside the DBN, and for all of these submodels, we have partial, sometimes complete descriptions. So in some cases, for small number of states, for sort of nice models, some trees, small naive Bayes models, this is done. We know everything, okay? And we can hope to just take that knowledge and translate it to the deep network case. In others, we just have some coarse information, like we know something about the dimension or the relative power or things like that. Kind of depends on how long it's been studied and how difficult it is. And of course, translating this understanding, the things we have, to something we can use or something prescriptive that says you should use this model for this kind of problem is, of course, an ongoing project, but one critical of the whole endeavor. So let's take a look now at some of these submodels, and I'll just say a few words about some of the things we understand about all of these things. Okay. So first is our naive Bayes model, which I said in the geometry land is called secant varieties or Segre varieties. In tensor land is called a tensor rank or a border rank model. And the string diagram is this kind of squid picture. And we've seen this before. So if I have just one biased coin, I want to think about that like a P1. So a P1 is, you can think about this as being, I have variables x0, x1, so points in R2 or C2, and I identify 2 points. I call them equivalent if they differ only by a single constant. And that's one way to define projective space, and I can make that makes sense too if I have more than 2 variables. But that's a P1, and that's very close to saying a probability distribution on a bias of a coin. It's just one-dimensional. Basically, I get to have to rescale so it sums to 1, but it's kind of the algebraic way of saying that. If I have a product of these things, then I have a Segre variety, and this is the nice case where I take flattenings of my tensor, think of it as a matrix in all possible ways, take all the 2 by 2 minors, and that cuts out the variety. So that gives me a complete algebraic description of it. If I take the first secant variety of this Segre variety, where I have two hidden states and 2 of each of these visible states, then that's also cut out by the 3 by 3 minors of the flattenings, and that remains true even when these things get bigger. But in general, it's not so easy. And we know things like dimensions, equations defining these things. Okay, so the expected dimension of secant k p1 to the n. So this is the naive Bayes model where the latent variable has k states and there are n binary visible variables. The expected dimension is min kn plus k minus 1 or the ambient space. So at some point it just fills up the probability simplex. Every possible thing is there, or at least it's full dimensional, and then it's just that dimension, right? You can't get any bigger than that, and you can figure that out by, for example, counting parameters. Okay, but as we've seen, especially for small n, or small models which are in some sense small, don't have a lot of n, sort of far from the limit, things can collide, and we get a defect where the dimension of the model is less than we would expect it to. So the freedoms we thought we had end up just folding into each other. And this will help us answer things like, is there hope for identifiability? Do we have fibers which are positive dimensional or just discrete, or what? And how big a model do we need to represent all distributions? So if we want to ask when is our thing a universal approximator, this is one way to answer that question. or at least not answer that question, but get information about that question. It gives you one direction. Okay, so this problem, what is the dimension of the naive Bayes model, was very recently solved. So some Italian geometers showed that it has the expected dimension, except in one single case where we have a 3-state latent variable and we have 4 binary observed variables. In that case, the dimension is 1 less than you would expect it to be. One parameter gets wasted because things collide. And so this is kind of the hard part in many of these things, is getting rid of the exceptions and showing that we know exactly where the exceptions are. This problem is over 100 years old. It was worked on in 1909 by Palatini. Then there was this explosion recently in sort of the late 90s and early 2000s where a bunch of people worked on this problem and made contributions to it. And that's partly driven by applications like statistics, machine learning, and other things to signal processing, quantum information, things like that. It's a very broadly applicable object. So anyway, we're excited that we're making progress on these things. And another way of saying this is that a generic tensor of C2 to the tensor to the n can be written as a sum of 2 to the n over n plus 1 decomposable tensors, product distributions, and no fewer. There's an ideal theoretic version of this thing. So I said earlier that in a nice case, we get the equations of this object, the secant of Segre or naive Bayes model, being defined by flattenings, minors of flattenings. So this was also recently shown to be true. As long as I have only 2 latent states, no matter how many visible states I have. So if I'm classifying something into 2 pieces, right? Yes or no, spam or not spam, and I have any number of variables, and I have any number of states in those variables, we can say what that ideal is now, what the equations are, and what the equations are in an ideal theoretic or scheme theoretic way, which is sort of a sophisticated way of saying what that is. And this work uses very heavy representation theory, or uses a lot of representation theory in order to understand what's going on, organizing this space of polynomials. Okay. So to summarize, equations of the naive Bayes model. So the simplest kind of model we can think about, the simplest component of a deep belief network or of a tree or many other things. So there's good news and there's bad news. The good news is we know for a small number of states what the equations are. The bad news is we don't know if we have large numbers of states. Okay. Making progress. Good news is that in some of these cases, the easy cases, it's just the minors of the flattenings. So it's just rank conditions on all the possible linear maps I can draw from this tensor. And the bad news, of course, that doesn't work all the time. But that always gives you some of the description. If you violate that, you know you're not in this set space. Okay, so good news is that many different models, tree models, restricted Boltzmann machines, deep belief networks, you can think about them as gluing naive Bayes models together in this way that I talked about in the beginning. I could take tensor products of things. I can take compositions of things. I can glue these things together, these models together. So we have some information, some cases very, very good information, like in trees. And the good news that we have above propagates to our understanding of larger models. And the bad news is that the bad news also propagates. Okay. Okay, so here's another submodel of a deep belief network, of a simple one called a hidden Markov model, right? So this is like, I took a deep belief network, I thought of it, I got rid of I set a whole bunch of stuff to 0 till it was a tree. I set even more stuff to 0 so that I was really only looking along one spine of the thing. And then even more so, I forced all the parameters to be the same. So that's basically a hidden Markov model as a submodel of a deep belief network. Here's a simplified version of that, just so I don't have to tell you all the parameters again. If I fix parameter matrices, so I choose one tensor, then up to global rescaling, I can think about the probability distribution as the sum of the trace of a product of these matrices. So the indices down here, A, I1, I up to IN, this index just keeps track of what the output state was, what the emitted state was in the hidden Markov model. So I take the trace of that product, multiply that by a standard basis vector. This describes a vector in if these are all 2 to the n, r 2 to the n, and that's a probability vector. Maybe I have to rescale it, but okay. And that corresponds to just a hidden Markov model where I require that the final hidden state is equal to the initial hidden state. Okay. So we would like to know what are the polynomial relations that hold among these types of coefficients. And that is the ideal polynomials in the coefficients such that everything it vanishes on the thing. So this thing has also been mostly worked out by a series of papers, sort of a not very good paper by myself and another co-author. It's good to be sometimes the first, even if it's not, right? And then some better papers by Schoenhuth and Critch and others that give, together these things give characterizations, membership tests, identifiability, and things like that that help us understand the hidden Markov model. And I'm working on a paper right now with Critch that exploits this, and I'll talk about that a little bit at the end. Okay, so the next submodel I want to talk about is trees. So this picture is a picture of a phylogenetic tree from Darwin's notebook. If you haven't seen this before. So he's sort of the originator of this idea. I don't think he was taking an algebraic point of view at the time, but people subsequent to that certainly have. I can think about a tree as taking a naive Bayes model and just gluing them together. So I glue a whole bunch of naive Bayes models together, tip to tail, and head to tail, and I get a tree. Right? Okay. So this was kind of one of the first. So this field of analyzing probability models from a statistical or from an algebraic point of view is sometimes called algebraic statistics, and this was kind of one of the models in which this stuff developed. There was a long series of papers by these authors and many others that address this problem of what is the variety of trees. So all of the, I should say, all the stuff on top is hidden. So all we observe, this is phylogenetic, so all we observe is the existing species, and we're trying to infer something about the history. The way to think about it is that, or the way the model works in the simplified setting is you think about these as being DNA sequences. So each of these things has four possible states, and I just pretend that every site in the DNA sequence is independent. So a whole sequence, if it's aligned, tells me, gives me a data point of many, many different realizations, and then I try to estimate the probability distribution that must have generated it, so thereby estimate the phylogenetic tree. So there's lots of ideas that make this stuff work, including change of coordinates, like switching to doing a discrete Fourier transform, switching to cumulant coordinates, constructions that use local information to get global information. There's a sort of a big theorem that says that if I understand how the equations of the naive Bayes model, the gluing works, and I can tell you what the equations of the tree is. So that's kind of like the best possible case where just knowing the local information is enough. And so we now have a complete algebraic description of many classes of the trees, and we even have complete semi-algebraic descriptions of this tree model called a general Markov model, so the different tensor at every node for small numbers of states. And this is a submodel. This is a bigger submodel of the deep belief network, right? It's kind of deep, but doesn't have there's no multiplication going on. Nevertheless, I'm hoping that this will tell us something about if we think carefully about it, about the possibilities for deep belief networks. Okay, so the next thing I want to talk about is restricted Boltzmann machines, but I think we'll take a break now and come back after that.